Now, the question here says a 250 millimeter depth and 150 millimeter width rectangular beam is subjected to a maximum bending moment of 750 kilonewton meter. Determine the maximum stress in the beam. Now, in this scenario, the first thing that we do is to visualize what you are working with. When you visualize it, it will be easier for you to work. So we have a rectangular beam, um here the depth is 250 millimeter and the base is 150. That is the width. The width is 150 millimeter. So let's draw the centroidal line. So the centroidal line that goes through the middle, so that is it. We can be able to get our y by getting d over 2, which is 125. That is the distance from here to here. That is our centroidal distance y. So that is it for that. Now, to get the maximum stress in the beam, in the beam, we use the bending equation. So we use m over I is equals to 5 over y. But we have our m, we have our y, and we have to get our I. So what is our I? I is equals to bd cube all over 12. bd cube over 12. So and bd cube over 12 is equals to um bd cube over 12. We have our base 150 times 250 cube over 12. So 150 times 250 cube all over 12. So if you do 150 times 250 cube divided by 12, we are going to get our answer. We are going to get our answer as 1.953 times 10 raised power minus 4 as our inertia. So that is for the inertia. Now to get the stress, phi would be equals to m times y all over I. Now m times y all over I, that is equals to our moment of inertia is equal to 750 times 10 raised power 3. Then our y, which is 125, we have to convert it to meter form, which is 0.125 divided by our I, which is 1.953 times 10 raised power minus 4. And then we are going to get our stress as we are going to get our stress as 4.8 times 10 raised power 8 Newton per meter square. And it can also be written as, if you take 2 zeros to the front, 1 2, it can also be written as 480 mega Newton per meter square. So that is the value of the maximum stress in the beam. Now, if the value find the value for if the value for E of the beam material is equal to 200 giganewton per meter square, find the radius of the curvature. In this particular scenario, it's easy. We just use E over R, let's say equals to M over I. Yeah, you can use any one of these. So we make R the subject of the formula. We have R is equals to EI over N, and that is equals to, we have E is equals to 200 giganewton per meter square, and giga is times 10 raised power 9. So we have 200 times 10 raised power 9. Then we have our inertia to be 1.953 times 10 raised power minus 4 times 1.953 times 10 raised power minus 4, then divided by moment of inertia, which is 750 times 10 raised power 3. That is the bending moment. So when we get all this together, our radius is going to be giving us our radius is going to be giving us 5.02 meters. So that is what our radius of curvature is going to give us. So now after that, for the third question, let's get into this. And now for the third question, we have to visualize this in order for us to be able to understand how we are going to solve the question. So now it says the value of longitudinal stress, which is tensile stress, of distance of 65 millimeter from the top of the beam. So now from the top of the beam, we are removing 65 millimeter. So if we remove 65 millimeter from the top of the beam, now if we remove 65 from the remaining 125 that is here, we are going to be having 60 millimeter. So now we are going to be having 60 millimeter as our y. Now from that place, we are from here to here, we are asked to find the longitudinal stress, that is the tensile stress that occurs at that place. So we just use phi over y is equals to m over I. So by doing, we have phi is equals to m y over I, where the m is equals to 750 times 10 raised power 3 kilo Newton meter, and our y now is this distance here, which is 60. So our y is equals to times 60, but here it will be in meter. Let's make this kilo first because the thing is per 3. Our y will be in meter, so it will be equals to 60 times 10 raised power minus 3 divided by inertia, which is 1.953 times 10 raised power minus 4. By dividing this, we are going to be getting 230.5 something mega Newton per meter square. Mega Newton per meter square. So that is how we get our shearing stress at this point here. Let's put it 5 prime y prime, since that is not the main centroidal distance, but that is the longitudinal stress from that point is given as that.